Hi, this is part 2 of the lecture on section 1.2, length and angle dot product, part 2 from the Math 311 linear algebra course. So section 1.2 is kind of a lot, there's a lot of material here, so I'm glad we're breaking it down into 2 parts. So last time we talked about the dot product and what its use is. Basically, it's a way of measuring the angle between 2 vectors in a given space, in a given dimension. And we actually defined the angle by defining the cosine of that angle, and we said that was the dot product divided by the product of their lengths. Okay, and just remind you that the dot product, this is u1 v1 plus u2 v2 plus un vn. That's how we define the dot product. Okay, we came up with this formula and just wanted to make sure that it is valid in the simple cases, the obvious cases when 2 vectors are parallel. That means one is a multiple of the other, right? So what we would have is, in this case, here's here's u and here's c times u, okay, where this is our v. Okay. What would the cosine, according to this formula, what happens here is that this would just, the cosine of theta would be u dot cu divided by the length of u times the length of cu. And in this case, we talked about this last time, that this we can, by the properties of the dot product, and since c is a real number, we can just factor that out. And we can factor out the c out of here. This is the absolute value of c times the length of u squared. And we can see that these actually cancel. The dot product of u is in fact the square of the length, so these cancel out. And so this is either going to be plus or minus 1. And of course, what happens, what angle has cosine equal to plus or minus 1? Well, it's going to be either 0 degrees or 180 degrees, which is what we would expect if they are parallel. Okay, so that kind of makes sense in this case. If u and v are perpendicular, as we have something like this, we haven't really officially defined what it means to be perpendicular, but let's just say we have two vectors in a plane, they're at right angles to each other. Well, in that case, this angle is 90 degrees, and we know the cosine of 90 degrees is 0. Okay, and so we can see that the only way that this can be 0 is if the dot product is 0. Okay. So that would mean that u dot v would have to be 0. And so we actually give a definition. Okay, instead of using perpendicular, we use a more sophisticated term called orthogonal, and we say that 2 vectors are orthogonal if their dot product is 0. And of course, what this ultimately means, though, geometrically, is that if you represent the vectors in a plane, they're going to be at right angles to each other, or perpendicular. So we determine just by looking at the dot product. So obviously, these 2 pairs, you have the dot product of this, 1, 0, and 0, 5. The dot product would be 0 plus 0, that's 0. So these are orthogonal. And if you take the dot product of these 2 vectors, you get 3 times 1 plus 3 times 1 minus 6. 3 plus 3 minus 6 is 0. So these would be orthogonal. Okay, it's pretty easy to see that these would be orthogonal in just the Cartesian plane. This might be a little bit difficult to sketch because they're in 3 dimensions. All right, now the immediate consequence of this is that we get the Pythagorean theorem. Okay, this is the Pythagorean theorem, of course, that relates the sides of a right triangle, A, B, and C. And of course, that would say that a squared plus b squared equals c squared. Okay. Well, now we can actually prove this. We can actually prove this using linear algebra. If we restate this using linear algebra, we can say if u and v are vectors, then we get this. Well, in this case, u could be represented by this vector going out here, and v is this vector, and then this would be u plus v. And the reason why this works is that it's actually pretty easy using the properties of the dot product, because we know that this it can be written as u plus v dot u plus v, and by the properties of the dot product, this is going to be u dot u plus 2u dot v plus v dot v. And we know that this is equal to the length of u squared, and this is equal to the length of v squared. Okay. So the only way that this can be equal is if this is 0. So we need to, if this is 0, then we have this. And if we have this equation, we see that u dot v must be 0, and so u and v have to be orthogonal. Okay. So that's a proof of the Pythagorean theorem. It's not real, actually, in a way, it's not completely self-contained proof, because if you remember last time, what we actually did is we used the law of cosines, okay, and you have to figure out, well, where did the law of cosines come from? And in a way, the law of cosines is a generalized version of the Pythagorean theorem. But anyway, that's how we can, that's the linear algebra version of the Pythagorean theorem. Okay. Now, there's a classical geometry problem that you may have seen before is finding the shortest distance between a point and a line. Okay, if you take a point that's a line and a point that's not on the line, we want to know how can we find this distance, the shortest distance. Okay, and I was talking to my mother about this morning, and she said, "Oh, well, that's obvious. You measure it." Well, that's true, but we need to do it. How do we use mathematics to find this? If we don't have a ruler. Okay. Now you might have seen this problem in calculus before, and they give you a formula for that. We're gonna see what's behind that formula, and we're going to kind of restate this problem. Is that we can actually view this distance as the length of a vector, and we can actually look at this as the sum or difference of two different vectors. If we take a point that's on the line and draw a vector connecting these 2 points, and then we have this line is going to have a certain direction vector, but if we can extend this direction vector to a vector such that that we can find, well, let's say if we call this vector v, we'd like to find a vector, two vectors that are orthogonal that add to v. Okay, where the first vector has the same direction of the line. And then we can find this distance was just going to be the length of that second vector. So we can restate this again, giving a linear algebra version. Given two vectors u and v, find two orthogonal vectors p and w, such that p is equal to lambda u for some real number lambda, and p plus w is equal to v. Right? Basically, this is the official name for this is the orthogonal decomposition of v with respect to u. And what we're actually doing is we're projecting v onto u. That's what this vector is being. We're getting this vector will be. We're getting a little bit ahead of ourselves. But let's just say, well, how can we find this real number lambda first? Well, so basically we'll remember that P, we want P to be lambda U, and we want P and W to be orthogonal, right? Okay, so basically here's the way we go. So we want P, the dot product of P and W to be 0. And we said P is lambda U. Okay. And in this case, we also want P plus W to equal V. Okay, so W is V minus P. V minus P, which is the same as V minus lambda U. Okay, so then this will be lambda U dot V minus lambda U equals 0. Okay, so now again we'll use the properties of the dot product. We can this lambda is lambda times U, and because we're using a dot product, we can basically factor the lambda out. Okay, and because lambda can't be 0. Okay, right? If lambda equals 0, then this is kind of this problem doesn't work, right? So that means that this must be 0. Okay, and again, using our properties of linear algebra, we can use our properties of the dot product and the distributive law. This is U dot V minus lambda and U dot U equals 0. Okay, so this means that you can simplify this as U dot V equals lambda times U dot U. So lambda is U dot V divided by U dot U. Okay, we don't have to worry about if the only way that U dot U is 0 is if U is the 0 vector, in which case this doesn't make any sense, this problem. So that tells us that P is this number times U, and then W will just be V minus this other vector. Okay, that's how we get those. And now we can see that everything is just in terms of U and V. All right. So with this first vector, that's the one that's parallel to U. We call that the projection of V onto U. Okay, and that's how we define this on the next sheet, on the next page. If U and V are vectors and U is not 0, then the projection of V onto U is denoted by this. And if, like we see, if W is the difference between V and the projection, then the projection and W are orthogonal, and we get this nice little picture to illustrate what's going on. Okay. So let's just give a few examples first, and then we'll see some neat applications of this. Okay, so in example 2, we have 3, -4, 4, 1. Those are our vectors U and V. We compute the dot product. That will be 3 times 4 plus -4 times 1, which I think is 12 minus 4. That's 8. And then we have U dot U is going to be 3 squared plus negative 4 squared, which is 9, plus 16, which is 25. So the projection of v onto u is going to be 8/25 times u, which is negative 3, 3 negative 4, which is going to be 24 over 25, comma, minus 32 over 25. Okay, we can leave it like this. And then w, we want to find what the vector that's orthogonal to that is. W would be 4, 1 minus this vector we just found. Okay, and you have to do a little arithmetic. And my arithmetic shows get a common denominator. I think this turns out to be 76/25 and 57/25. And you can check that indeed that these two are orthogonal on your calculator, or you can first factor out the 1/25. You'll see they're orthogonal. The dot product of these will be 0. Why don't you take a moment, if you want, you can pause the video and do this next example. The same computation, except it's in 3 dimensions. So u dot v is going to be 6 minus 3 minus 10. Okay, so this is going to be, if my arithmetic is right, it should be negative 7. And then u dot u is going to be 14, right? Because we get 1 squared plus 3 squared plus negative 2 squared is 1 plus 9 plus 4. That's 14, right? That helps out a little bit because negative 7/14 reduces to negative 1/2. So our projection is going to be negative 1/2 times 1, 3, negative 2, or negative 1/2, negative 3/2, positive 1. And then the w vector will be 6, negative 1, 5, minus negative 1/2, negative 3/2, 1. Okay, which I believe, let's see, again doing some fractions, this is 6 plus, this is 12 halves plus 1/2, that's 13 halves. Okay, negative 1 plus 3 halves, that should be 1/2. And then 5 minus 1 is 4. Okay. And once again, you can check that these are orthogonal. Alright, so it's a very straightforward computation. Now, it's not too hard when you have the formula right in front of you. Okay, well, getting back to the original, the classical geometry problem, how do you find the shortest distance between a point and a line? Okay. Well, you can start by drawing a picture, see the situation. Okay, so here's 5, 3. And we're just going to pick the easiest point we can find on the graph. This is the line y equals 3x minus 2. The easiest point we can find is we can just plug in any value for x. So we'll plug in x equals 0 and then y is negative 2. Okay, and we'll let this vector be v. Now the direction vector, the direction vector is not unique. We can basically pick any point on the line, and that will work. So I'm just going to plug in x equals 1, and that gives us 3 minus 2. That's 1. So we get the point 1, 1, and that will be our u. Okay. right, so we can see that u is going to be 1 minus 0, that's 1, and 1 minus negative 2, that's 3. So that's u. And then v will be 5 minus 0, that's 5. 3 minus negative 2, that's going to be 3, plus 2, that's 5. Okay, and I think, yes, that's right. Okay. Now what we want to do is we want to find this projection. Well, first we're going to find the projection of v onto u, and then we're going to find this vector w, and then the distance will be the length of w. Okay, so there are 3 calculations we want to make. So the projection of v onto u is going, the dot product is 5 plus 15, so that will be 20. And the length of u, and then the dot product of u with itself will be 1 squared plus 3 squared, that's 1 plus 9, that's 10. Okay, so this is going to be, this is 2, right? Okay. And so, actually this is, I should say, this is a scale, which we need to multiply this by u, and so this is going to be 2 times 1, 3. So the projection will be 2, 6. Okay. All right, and then w will be 5, will be v minus this projection, so it's 5, 5 minus 2, 6, which is 3, negative 1. Okay. So we find out that the distance, and then finally the distance is what we're looking for. The distance is the length of w, which will be the square root of 3 squared plus negative 1 squared, which is the square root of 10. So that's what this distance is. And notice that at the same time, we've actually also located the point here, that is the point on the line that's closest, right? Because all we have to do is start with this point. The vector from here to here is the projection. So we take the coordinates 0, negative 2, and we add the projection, which is 2, 6. Okay, and then this actually is going to be 2, 2, 4. All right. So that we also get the closest point on the line. All right. Again, you may have seen this before. There are some nice formulas that in calculus books that give this to you, but this is where this comes from. Okay. One last example here is finding the area of a triangle with given vertices. Okay. We can do this again by looking at writing this problem in terms of vectors. And remember, thinking of a triangle can be written as the one side of a triangle can be written as the sum or the difference of 2 other vectors. So let's look at it here. Let's say we have, I won't draw this to scale, but we have 1, 1, 3, 5, and 6, negative 1. All right, I'm going to draw a vector connecting these 2 points. I'm going to call that V. I'm going to draw another vector connecting these 2 points, and I'm going to call that U. Okay, and then of course we can if we wanted to, we could complete this. Okay, this I guess would be V minus U, or okay, so there's our triangle. Now, if you remember, the area of a triangle is 1/2 times the base times the height. All right. Well, what's the base is nothing more than the length of U. And the height is actually going to be this perpendicular vector that's orthogonal to u that adds up to v. Okay, so the base, as we said, is the length of u, and the height, well, is going with this, it's the length of this distance, is the length of this vector, which we said this is going to be the length of v minus the projection of v onto u. Okay. And okay, so we should be able to figure everything out. Let's first of all find what u is. U is going to, the coordinates of u will be 6 minus 1, that's 5, and then negative 1 minus 1, that's negative 2. Okay. V is going to be 3 minus 1, that's 2, 5 minus 1, that's 4. And then we can see that u dot v will be 10 minus 8, which is 2. And u dot u will be 5 squared plus negative 2 squared, that's 29. So this projection is going to be 2 over 29 times v, or rather times u, which we said is 5 negative 2. And then v is going to be, v is 2, 4. Okay. All right. If you do the arithmetic ahead of time, okay, and are good with your fractions, you find that this vector turns out to be 48 over 29 minus 120 over 29. Yeah. I'm sorry. There's no minus here. I'm getting ahead of myself. 48 29ths, 120 over 29. And so the area then is 1/2 times the base with the length of u. The length of u, you could see, is the square root of 29. Okay. And then the height is going to be the length of this vector. Okay. And then you can use a calculator, or you try to simplify this with algebra, and then use your calculator, and amazingly this turns out to be a nice integer, 12. Okay. So that's the area. Okay. All right, so this is a very nice application of the projection. Okay. We're going to be using this with this projection again and again during the course. So again, you can go and study this, take the mini quiz, do the homework, and I will see you next time.